Hello friends, today we are going to carry on with the second edition of our discussion on projectile motion. So, care for a spoonful. Now, you must be thinking, what has a spoon got to do with projectile motion in general? But projectile motion is just that. Even this is projectile motion. So, whatever you can throw in the air and whatever that comes back, it is undergoing projectile motion. So, even a spoonful of projectile motion can be something that you can look forward to when you have to clear out your concepts on this. Now, before we have got our discussion on it, and I've tried to clarify some of the concepts to it, today I'm going to add on to those concepts in a way, in a small way, and we'll see whether we can discuss some other problems related to it. So here it is. Let's begin our discussion on projectile motion. Now, before we do that completely and in detail, of course, this is based on understanding that you are completely okay with vector resolution in general. If that is fine, then this discussion is going to make sense to you absolutely. So yes, this is our discussion on projectile motion part 2, and let's see what we had done before. We had discussed with respect to this problem most of the concepts with respect to projectile motion. The only thing that was left for discussion was range. Now this was where we had stopped the previous day. So let's just complete discussing this, and then we can move forward with our today's discussion. Now the range, as you can see, that it was given by the product of u cos theta and time. The time was found out the previous day. It was uh, it was given as, if you can take a look, it was given as the product of 2u sine theta by g. So if I try to incorporate that in this expression, then what we get is something like this. So from here we can get the range, or the maximum, or the distance along the horizontal direction that the projectile travels. Any object which is executing projectile motion travels. So this is the expression of range that we have got. Now, a bit of variable manipulation will enable you to understand that you are looking uh, at the expression of 2 sine theta cos theta, which means it can be expressed as sine 2 theta. So if I try to do that, then the range becomes something like this. So this is the expression of the range. Now, of course, the maximum value of sine of any function is, it is 1, which means that over here as well, the maximum range can be obtained just by tuning the angle. So, when is it that you get the maximum range? Or first of all, what is the maximum range when that sine 2 theta that gets the value of 1? So obviously, if I try to write it, the maximum range is something like this. There's no issue with that, I hope. But certainly that happens when you have this particular condition being satisfied. That means when this 2 theta is 90. Now, what happens when 2 theta is 90? Obviously, then you have the angle of projection to be 45. So when you have the angle of projection to be 45 degree, uh, then you can consider that the projectile will reach its maximum range. So this is an interesting part of the discussion, because you get to understand that even just by changing the angle, you can change the very distance along the horizontal direction that the projectile can travel. So in fact, this is what athletes performing in an Olympic event try to do. Can you guess what is the Olympic event that I'm talking about? There are many kinds of events, but something that comes to my mind right now is javelin throw. So the athletes who are practicing it, obviously, they can throw only with a particular maximum velocity. So when they are practicing, what they look for is just to throw at that specific angle where the maximum range is achieved. So this is what I think the power of physics brings in. So when 2 theta is 90 or when theta is 45, then you have the maximum range possible. So this is an interesting fact, dear friends, where uh, you can use this to maximize the distance of travel instead of let's say if there is a requirement that you want to travel higher up, obviously there also you can use this expression of height. You can see that it gets the maximum value only when sine theta is 1 or when theta is 90. So from there you get to understand that if you throw it vertically up, it will reach the maximum height because there's no energy that's used in covering the horizontal distance. So from there you get to understand, as we had discussed in our previous video on projectile motion, that certainly vertical motion with gravity is a special case of projectile motion. In fact, both these two things are to be studied not separately but simultaneously. That is what I do when I'm teaching my students, that I try to make them aware that apparently disconnected topics are actually not so. In most of the cases for physics, the topics are extremely related to each other, except for a few exceptions, of course. But those are very, very few. And once you get to understand this, which I try to make the students understand when I'm teaching them online, once you get to understand that, you really can see physics in a completely new, different way. So that is my endeavor through these videos and through online tutoring that I try to achieve. So yeah, let's proceed from here. So yes, we have understood that the maximum range would be this when, and this would be achieved only when the angle is 45. The angle of projection is 45. Okay, now let's move on to our. So this was our basics for understanding projectile motion. Of course, how is it that we can be assured of that we have understood the basics? If we can apply the basics, then we know that we have understood them. So let's see whether we have really understood them or not. Let's check another problem and see what we get. This is also again a question taken from an IB question, IB previous year paper, and in fact, this is also applicable for anybody who is studying in this level, in the high school level, be it a class 11 student from any board. I think this is applicable for him or her. So let's just look into the problem. You can see that there is a projectile that has been launched horizontally. So if that is the case, then you can understand that the initial vertical velocity is zero. Mind you, if you refer to our previous discussions, the vertical velocity initially was taken as u sine theta in this expression. That is zero over here because the object has been fired horizontally. So initial vertical velocity is zero. If that is the case, now take a look into this graph. It is interesting to note that they have given you a graph of kinetic energy per unit mass. Now you know what is kinetic energy. It's half mv square. So if it is per unit mass, you definitely get half v square. So there you have been given an expression of how v square varies with vertical displacement. Now, this is what I do, that when I normally explain a question to my students when I'm tutoring, I try to understand whether the graph that is given can be verified theoretically. So first, let's try to do that. In fact, it is my plan that I will also go through some questions specifically on graphs, because that is what I feel many IB students struggle with. uh, they do not know how to analyze graphs, and I need to discuss that in detail. But before that, let's try to go through this. So first of all, let's try to understand how is it that the total energy, the velocity, how does that vary with vertical displacement? Now, mind you, over here, the total energy is composed of both the horizontal kinetic energy and the vertical kinetic energy. So here the object will have two velocities, horizontal and vertical. Horizontal velocity does not change, whatever that is. vertical velocity obviously changes. So from here, let's try to understand how we can get an expression of the total energy versus the displacement. Now, for that, we'll have to understand how we can arrive at an expression of total or resultant velocity square. Kinetic energy, you see, it is half mv square. That v is the total velocity or the resultant velocity. So here we have to arrive at an expression of the result of the square of resultant velocity with vertical displacement. Let's see how we can do that. So now the resultant velocity square should be if you can think of it in this way, that it is the resultant of the horizontal velocity and the vertical velocity, then it should be written as the way vectors are written, the resultant vectors are written in the same way. Try to guess it how you should be able to know it if you have gone through vector resolution. So first of all, this is how the resultant velocity should be written. Now Vx square we don't know, that is what we have to find out. Vy square obviously we do know, because we can use the expression of v square equals u square plus 2as, the conventional equation of motion, to express this, and that should be written as something like this. Now mind you, over here I'm using that expression to for a particular direction. In this case it's the y-axis. So this is one thing that you have to keep in mind, that when you are using the third equation of motion, if this is the case that you have to use it in particular axis, this is how you use it. So if you refer to the equation over here, the vertical velocity is the vy square, that has been replaced as 2gd, because if I try to use v square is u square plus 2as along the y direction, y being the vertical direction, then the initial velocity is 0 along the vertical direction. Mind you, over here you can see that the object was fired horizontally, which means the vertical velocity was 0 initially, which is why along the vertical direction initial velocity is 0. Now from here we get this expression. I hope this is fine. Now in this case your expression along the y-axis is just uh, kinetic energy per unit mass, which means that we should be along the y-axis you are having the expression of half v square. Mind you, because kinetic energy is half mv square, per unit mass means half v square. So let's find that out, and then let's see what we get. So what we have to do is that we'll have to divide this entire thing by 2. So let us try to do that and let's see what we get. So yeah, let's try to do this. Yes, so something like this will happen. I've just divided by 2, and then left hand side you can see it is just v squared by 2, which is nothing but our y-axis variable e, that is kinetic energy per unit mass. So this has been done very very subtly, I would say. So what you get along the x-axis is displacement, as you can see, and if that is plotted with displacement, you can see that it's going to be a y equals mx plus c kind of graph, where the c or the y-axis intercept is given as bx squared by 2. Just take a look into this graph. See, let me try to break the terms into the two parts so that there is no issue with understanding it, and then I think you'll feel more comfortable. Over here the left hand side is given as e. Mind you, it is not the conventional kinetic energy according to the problem, it is the kinetic energy per unit mass. So this is what you have. Look into this. So the displacement, vertical displacement, that is the x-axis variable. Along with it, you have 2g by 2, or rather it is g, and the intercept is given as vx square by 2. So obviously that intercept is given as 900, which means our vx square by 2 is 900. So our vx square should be 1800. That is what we get to understand. So that is our first conclusion about the question was you have to find out the initial horizontal speed, and we have got the square of it. You can get the square root and you can arrive at the result easily. The next thing is how you can arrive at the time to hit the sea. Now when the projectile hit the sea, the final energy per unit mass was 1300. So take a look into this. If it was 1300, then that was v squared by 2. So the final velocity square should have been 2600. See if you can understand this. The final, you can take a look that here you can take a look that v squared by 2, this part is our e, and that is given at the time of hitting the sea was this much. Take a look, it was 1300. So if v squared by 2 was 1300, certainly v square would be double of that, which is 2600. So let's try to write that v square is 2600. If that is the case, then from there we can find out the vertical velocity, because it's you know the resultant velocity square is the sum of the squares of the horizontal velocity and the vertical velocity. We have the horizontal velocity remaining unchanged. Again, keep this in mind, it's only the vertical velocity that changes because of experiencing acceleration due to gravity. So from there we can find out the vertical velocity square, and let's try to do that. Over here, if we just subtract it, 2600 minus 1800, how much will you get? How much? You know that 800. That's going to be your uh, vertical velocity square, and if you do the square root of that, you will arrive at the result of vertical velocity. So if you just do this, you'll get a particular value, which is if I do it, you'll get it something around 28. So this is the vertical velocity with which the projectile hits the sea. So this vertical velocity obviously would be equal to, again we can use v equals c plus at. U again is 0 along the vertical direction, along the y-axis it is 0, mind you, again because it was fired horizontally. So this should be written as u plus gt, or u is 0, so it is just 10, considering u g to be 10, we have dy to be 10t. So from there, if we just equate the two, we'll get t to be equals 2.8, and that is how we have our answer of the time to hit the sea. So here I've tried to go through multiple concepts. If I have to summarize this, here I have tried to first explain how you can analyze a graph. Do not try to analyze a graph without getting the expected nature of the relation. So here I've got the expected nature of relation between kinetic energy per unit mass and the vertical displacement. This is how you do it. From there, we have been able to arrive at the vertical velocity, and from there the resultant velocity, and also combining these two, we have got the vertical velocity and the time. So all these factors so very intimately related to each other that if you are not comfortable with any one aspect of vectors in general, you'll not be comfortable with projectile motion. But this is just one of the problems where I try to explain as many concepts as possible. So I hope this was helpful for you, and I hope that you got a taste of a spoonful of projectile motion. I hope that I really do hope that I can I can add more tastes to your taste buds in future with these kinds of videos. And this is what I normally do when I try to explain something. I try to take a question. Normally that question, if it's normally if it's an IB question, you'll have multiple other questions involved in it. It's like it's like interesting like onions. It has layers. I try to go through the layer one by one, and in most of the cases that is helpful to the students. So this is something that I've tried to do over here as well. I hope you liked it. If you have anything to comment, please let me know. And certainly for one-to-one help or online physics tutoring, please let me know. The email ID is in the description box. Let me know what you thought about it, and we'll surely continue tending your taste buds not only with the spoonful of motion, but with other tasty concepts as well. Thank you, everybody. Have a great day, and see you after some time. Thank you all. Thank you for your time.